So this talk is about iterators, if you haven't guessed yet. I gave a similar talk at a London functional meetup, where I talked about coroutines and continuations and stuff like that. That was a bit more technical, so I extracted some more interesting ideas, core ideas from that talk, and rewrote them in Reason. So today I'm going to be presenting two different, almost opposite models of iterators. And I'm going to show you some examples. I'm going to show you how to actually implement those iteration models in Reason without any libraries, without any special language features. Just a quick introduction about myself. I'm a platform architect at Pusher. This is Pusher, by the way. We use Reason at Pusher. We mostly use it with the native backend, so almost like OCaml with Reason syntax. And our project is essentially a data processing analytics pipeline. We implemented some of our metrics in Reason. If you're interested in that, just feel free to grab me after this talk. I can talk more about that. So yeah, I've been using OCaml for 4 years now, and I started using Reason on the day one when it was released. I was super excited about it because I'm a language designer myself, and I was building a relatively similar language at that time. I'm also very interested in streaming, iterators, and coroutines, and that kind of explains this talk as well. So many problems can be solved with iterators. Streaming problems are everywhere around us in programming. We might not see some things as streaming, but in reality, I think even some things like, for example, functional reactive programming can be described as streaming. I'm not going to talk about that specifically, but I think most people probably know about that. So why are iterators useful and interesting? For me personally, it's because they allow us to replace imperative for loops with something that is more composable and sometimes even more efficient. Essentially, if we have a for loop and we want to write an efficient code, then we need to just literally write everything in that for loop. Otherwise, we will probably sacrifice performance. But with iterators, what we can do is preserve this composability of like modular design. We can write different units and compose them together without paying too much for that specifically. So this line here, I think, is essentially the core idea behind this principle. On the left, we have something that applies the function f and g with the map combinator. So we essentially apply this function to the elements in the list, but we do it twice. What's happening there is map g list is producing a new list, and then we say map f over that list. And essentially, we have to traverse the collection twice, and we need to allocate that collection twice. While in the second case, what's happening is that we just took these two functions, f and g, we combined them, we composed them, and we run the map transformation only once in the list. So this is like the core idea behind iterators. We can think about them as non-blocking collections or like streams. And many modern programming languages adopted iterators and put them in the center, at the core of the language design. Languages like Python, Ruby, C++, JavaScript, or even like Rust have iterators, and they have very good support for iterators. But what about Reason? Well, Reason doesn't really have iterators. At least there's no built-in support for them. But that's fine. We can create them in Reason without any changes to the language, which is super awesome. So again, I will be talking about two different models. Let's start with something simpler. Let's just look at iterators in JavaScript. So this is a simple range iterator. It conforms to the protocol, the iterator protocol, which is really just a convention. And the only thing that it needs to do is say that it is a symbol, it has the symbol .iterator key to indicate that it's an iterator. And it has the next function, which will produce the value for the consumer of this iterator. The way it's done is quite interesting. Our function, next function, returns a pair of values. It returns the done flag, which is a Boolean, and the value itself. And while our done flag is set to true, we know that we have values to consume. But once it's set to false, the computation is essentially finished, and we need to stop. And JavaScript has a built-in syntax for iterators, which is also very useful. So we can use that range iterator, create the iterator itself, and iterate on all the numbers produced by that. And of course, that's just going to give us 1, 2, 3, 4. There's a simpler way to write iterators in JavaScript, and that can be achieved with generators. So generators are really just an easy way to write iterators. It's a special built-in syntax that translates a simple code like this into something that implements the protocol that I showed you previously. So yield is a keyword in English in ECMAScript 6, and it essentially will handle the publishing of this value to the consumer, and it will suspend the state of this iterator, and it will resume the state once the consumer calls the iterator again. And again, we can just simply use this value in the same way. So there's no actual difference between iterators and generators. Generators are just iterators with better syntax. So before I explain iterators in Reason, let's just go back to something very, very simple, like just the fundamentals. What is iteration about? What is the essence of iteration? And for me personally, it's as simple as a function. So we can start with functions. What do we need from functions? We need to, well, iterate on values. So we need to get values from functions. There's a type for that. So this is not an actual Reason or OCaml syntax. I simplified it a bit. But essentially, this is a function that once called will give us a value of some type. We can continuously call it. We can call it multiple times, and we will get the value every single time. So it's essentially a producer. We can pull it. It's almost like a pull-based iterator. We can pull it, and it will give us this value. There's one issue with this function if analyzed from this iteration perspective. Can you tell me what it is? What do you think is the problem? Yep.
What if it runs out of A's?
Yeah, exactly. So what if it runs out of A's? What if the iterator is limited, so it has a specific fixed number of things? How can we, say that it's done? When I, the consumer, don't need any more values, I can just stop calling this function and I'm satisfied, I'm done. But what if the iterator terminates because we exhausted the collection, or maybe because we're reading lines from the standard input and we got end of file or something like that? So how can we say that it stopped? Well, we could use an option value type or something like that to signal this termination, but what about exceptions? So if I try to call this function and it doesn't have any values to give me, it can just raise an exception. And that's acceptable, that's fine. I'll try to explain later why it's fine, why I think it's fine. And I will also show you the implementation with options. But for now, let's just see what happens. Let's just use exceptions. Let's just use this specific model. So we define this iterator type that is the same thing that I showed you. So it's a pull-based iterator. We need to ask for things to get them. We define the stop iteration exception that will be used to indicate the termination of the producer. And then, we need some state. Let's implement a function called count, for example, that will produce a sequence of numbers up to a specific end. So for that, we need something like a current value, current count, and that's going to be a reference, a mutable reference. And our count function will look like this. So we have our reference. Notice that the count function has the type of iterator. It's not explicitly stated there, but it's structurally compatible with that type. So it's a function from nothing to a value. In this case, it's an integer. So what's happening here? Well, we we dereference the current value with that trend symbol to get the actual n. We check if that n is greater than or equal to 3, and if it is, we just stop. Explode the world and just stop. And after that, if that's not the case, if n is less than 3, we increment our current value and simply return the previous value before we incremented it. So that's going to be like 0. So, and we can immediately start using this iterator. It's a very silly and simple iterator, but I think it's an iterator. So we can call it multiple times, and once it reaches 2, the next time is going to be stop iteration. So we terminated this iteration. Okay, so what do you think about this? This is functional programming, exceptions, mutable state, global variables. I guess that's not what you came here for. Let's see if we can improve things a bit. But the interesting thing here is that in Reason, this is not actually an issue, and I'll explain why. So let's go back to our pull function without the option type, and let's add this option type. So instead of using exceptions, we will now use the option type, which is slightly better from like a conceptual perspective. It does have one issue though. Option types, at least in the native compilation toolchain, have a relatively high cost. So every single time you have a value, it has to be boxed essentially in this option type. I think the same applies to JavaScript. I run some benchmarks that I will show you in the end, and the results are quite interesting. Okay, so let's use this type to implement our conf function and see what happens. So this time I'm not using global variables. I'm putting this current mutable value within the scope of the closure that is returned, but it's still this iterator type. So it's almost the same code. The only difference is that instead of rising an exception, we say none, and we wrap our count value into the sum constructor. And of course, we can just call it, and we will get some 0, some 1, some 2, and then none. So this way, we know that the iterator terminated without having to handle that exception. Seems like an improvement. Okay, so, but this, what does it have to do with iterators? Is this what we want to do? Well, I feel like there's one thing that I need to explain, and I hope that you will understand why this kind of code, mutable code that uses exceptions, is actually quite acceptable in Reason. And the reason behind that is interfaces. So interfaces are a very powerful way to describe abstract computations, abstract logic in general. So here we have the module type Iterator Interface. The type T is essentially like the type of the interface, which is iterator. You can think about it as this for that scope. And I listed here, enumerated here, a few functions, helper functions that are typically seen in iterators, like map, filter, take, and fold. Just to give a quick explanation of what each one of them does, essentially map takes a function that can transform some values, and it translates the iterator of types of values of type A into an iterator of values of type B. Filter can ignore some values by having a predicate function that essentially says, no, I don't want this value. When it returns false, it means that we are not interested in that value at all, so just ignore it. Take is quite interesting because it limits our iterator. It has the power to say, I'm only going to publish n elements, and after that, I'm done. So essentially, it would raise an exception or use a none value to indicate that. And finally, fold is a very useful combinator that allows us to essentially compress an iterator into one single value using this stepping reducer function. Okay, so what's so special about this? Well, this is abstraction. This is something that allows us to think about iterators in a very general sense without having to commit to a specific implementation. So this is something that just describes what we want to have, but it doesn't give us any specific implementations. So, and if you have something that implements this interface, regardless of the implementation, you can be assured, you can be safe that nothing bad is going to happen. Because do you see any mutations here? Do you see any exceptions? All of that is essentially protected by this interface. Okay, so now that we know that, let's try to implement this interface with our original pool iteration type. This is the map and fold functions. I think the implementation is very straightforward. So essentially what's happening here is that we take our iterator as an argument in map, and since we know that it's a function because of that specific type declaration, we can simply call it and see whether it has a value to give us. And if it doesn't have, well, that's fine. The map itself, which is an iterator, is going to terminate too. If it does have a value, we simply need to obey the type and wrap it into an option and apply F to perform the transformation. And fold is very straightforward too. The same thing happens here. We check if the iterator has any values for us. If it doesn't, we simply terminate with the initial or the accumulator value so far. If it does have values, then we use the F function to compress that value into the next one. And we continue recursively. And with this 2, 3 functions and a type, we can already start writing some pipelines like this one. So that symbol here is a pipe operator. It's essentially a function application. In this case, it's going to take count 3 as an argument and put it right there. Map will translate every single value that passes through that iterator, and finally fold will wait for all the values and sum them with a plus operator, so we get 33 in this case. Okay, so as I said, there's a problem with this approach because it might be slow in some cases. Okay, so I promised that I would tell you about 2 different iteration models. And as it typically happens in computer science, there's always like this opposite model, dual model that in which everything is essentially inverted. So if we have this pool type that is a producer, how can we get the opposite of that? If that one was producing elements, the opposite has to consume them, right? Now, this is a push. This thing can be used to implement a push-based iterator, something that essentially consumes values. But how can I use this to implement iterators? I can give it something and it doesn't give me back anything. It's like a black hole. I just keep sending stuff, but nothing comes out. That doesn't seem very useful. But if I have a consumer like this one, I can pass it to a producer. And that producer might be able to give it some values, and that can be useful. So this is the final type of our push iterator. It might look complicated, but this is just 2 functions, really. It's just one function taking another function as an argument. There's no magic here. It's just regular types and values. Okay, so let's see if we can build something with this abstraction here. We can define the consumer type, which is something that takes a value and does nothing. Unit means nothing. And our iterator, in this case, is something that takes a consumer and does nothing. So let's look at an example of our count function implemented in JavaScript with generators. So here we have this count function, or a generator because of the star symbol after function. It's a simple for loop, and then it just yields the values up to a given n. What can we tell about this yield keyword? It seems very special. The first time I learned about iterators, I was like, what is this yield? Like, it just seems so strange. Like, how is it different to return and so on? What is its type? Does it have a type? Well, as I was researching this specific iteration model, I was quite amazed by how my understanding of this specific pattern improved by learning this iteration model. Let's look at this equivalent implementation in Reason. So the body of the function is almost identical to our JavaScript example. As we can see, there's a yield, there's a for loop, we just iterate and yield values. But the difference is yield is not special anymore. It's just an argument, and it happens to be a function. And count is an iterator that matches that type there. So yield is a consumer. And we essentially just, recreated this iteration model from scratch. I think it's pretty interesting. And another interesting thing to notice is that yield is essentially just a callback or a continuation. We supply this function to receive the values, and the producer will do something and generate these values and send them down. So let's use this function. We can create this numbers iterator that will only count up to 3, and then we need to give it a consumer that satisfies the consumer type. Well, the easiest one is actually just gs.log. If you look at the type of gs.log in buckle-script documentation, it literally is our consumer. It's the same thing. And as we call nums with gs.log, that gs.log is our yield. So we are essentially just iterating with a for loop and logging things. OK, so how would we implement other functions in our original interface with this? This is the implementation of map. So yield is still an argument. It's not special. We receive it, and we know that it's going to consume the values somehow. It doesn't really matter what it's going to do. We just know that we need to send them down to that consumer. That's our only responsibility in map. But iter itself, look at the type, is a function, right? Iter itself is a producer. And we saw here that if we pass a consumer to our producer, things happen. So in this case, if we call iter, which is our producer, with that new function, we know that the final iterator itself will use that consumer, right? And in this consumer, we're intercepting essentially that consumption instance, and we are applying f before it actually consumes the value. Right before we consume the value with yield, we apply f. Let's look at filter. Filter is very easy. Filter is essentially, do you want to consume? If we have p, which is a predicate, to test our value for inclusion in the iterator, in this new consumer function, we check is px true, and if it is, yield. If not, just don't do anything at all. OK, so fold is interesting because fold requires us to use mutation. We have this consumer that we pass to iter, but there's no way for us to extract any values from it. It's a sink, essentially. It's a black hole again. So we know that whatever we put inside that iterator, consumer, will happen, but there's no way for us to extract values. Well, turns out there is by using mutation. So if we pre-declare a result reference, and then in our consumer, we continuously change the result reference, we know that in the end, once iter itself, the producer, is finished, we have the final value. So that's our fold. And we, of course, return the final result dereferenced. Another function that I had in my interface was take. And take is very tricky because it requires us to use mutation and exceptions. So in this case, I separated the consumer into a step function. Essentially, it's a consuming step. Downhill in the final statement expression of take, we call iter with that step function, and we wait for stop iteration exceptions. And the step function itself will receive the value, will consume the value. It will also check the state of take to see if the count reached our limit n. And if it haven't, well, in that case, we need to update our count and let the yield consume the value. Otherwise, we stop iteration. But the thing is, this stop iteration exception is only available here. We know that we handled it. So it's not going to leak out into the other parts of our code. It's completely contained in this function. There's no risk of getting unsafe exceptions. So I run some benchmarks with these different models. I compared them with the standard JavaScript implementation. I used both push and pull based iteration models that I showed you here. And for the pull-based model, I used the one with options and the one with exceptions. This is the basic benchmark that I came up with. It's very simple. It doesn't really do anything useful, but it applies our combinators multiple times just to make sure that we have some diversity here. And these are the results. So blue is our standard iterators in JavaScript, the ones that I showed you in the beginning. Red is our push-based model. Yellow is pull, and green is pull with exceptions. As you can see, our red, which is the push-based model, the last one that I showed you, is consistently more efficient than even the standard iterators. I find this very interesting because it's the same language. It's still JavaScript. All of this just compiles to JavaScript. And of course, we can implement the same model in JavaScript, but the one that we have in the language is slower than this one that I just implemented, and it's not that complicated. So yeah, back to our types. We have pull-based iterators with option in this case, and push-based iterators. Sometimes they're called external and internal iterators. And why do we need both? Like if this one is more efficient in that benchmark, why do we need the external iterators? Well, there's always a trade-off, right? Like in this case specifically, there are some things that we can do with external iterators and some things that we cannot do with them. For example, zipping multiple iterators at once is hard, if not impossible, with internal iterators. And splitting one iterator into multiple iterators is almost impossible with the external iteration model. So I guess we just need both. If you want to use this iteration models, both of them are implemented in OCaml libraries. They're compatible with Reason. There's no special, there's nothing special in them essentially. They're just essentially the same code that I showed you today, so they can easily be compiled to JavaScript with Reason. I also wrote a very simple pull-based iteration library, which is entirely pure and doesn't rely on exceptions. It's essentially a mixed approach that I came up with based on both the push and pull-based iteration models. So just to conclude, what we have learned here was that iterators don't really require any special language features. We can quite easily build them if we have a powerful enough language. Pure-ish programming is possible in Reason and OCaml. If we have strong types and interfaces, essentially we can afford having mutations, exceptions, and all of that imperative stuff completely protected from the rest of the code because the interface is there to make sure that it doesn't leak. And also, impure functional code is possible. So we can have impure, dirty, performance-oriented tricks in our functional code. That's very interesting too. And of course, functions are the ultimate abstraction. That's the conclusion of my talk. Thank you very much.